Nicolaus actually was introducing our paper, in effect. So there are a lot of things that are very relevant here. So in fact, what we're going to say is that, among other things, that an outgrowth of this Hilland and Zeckhauser mechanism, which actually several people have independently had the intuition for, is actually the kind of thing that Nicolaus was talking about. So, and it's certainly both in the broad sense a quadratic voting, but we also want to show that in a narrower sense that the quadratic voting in the simple public good case that Glenn was talking about is actually a special case of the normalized gradient addition mechanism. So I need to introduce things a little bit more. So we came at this from the subjective well-being literature. So the idea there is to measure happiness, meaning in life, and to try to figure out what that tells you about what you should do about public policy. And one of the problems there, so in that literature, there are some wild claims by, for example, Richard Layard, that somehow subjective well-being data will magically solve this problem of interpersonal comparison, which patently isn't true. You still have all the issues of interpersonal comparison and social choice that you do without subjective well-being data. And so we came to this as a way of trying to deal with the social choice problem with the subjective well-being data. So what kinds of things do we want from a social choice problem? We know that economists certainly have been historically very excited by the first welfare theorem, that competitive markets are Pareto optimal. So you clearly want to have Pareto optimality in your social choice mechanism if possible. But of course, in the competitive equilibrium, there are issues like distortions and Pareto optimality only over market goods. People worry that it favors the rich. So if you come to the mechanism we're talking about, the iterative normalized gradient addition mechanism, which we have a couple of papers. This one, so that's Benjamin, Heffitz, and Kimball. So Dan is here, and Ori Heffitz is off in Israel. And then Nicole Zembrot, and then this one is with Gabriel Carroll as well. The nice thing about this is it'll yield Pareto optimality constructively. So you can use data in principle to do evidence-based government, get to Pareto optimality constructively. The effects of distortions and informational problems can be built into the structure of the policy space. So you worry about tax distortions, you build them in to the structure of the policy space to account for them. The Pareto optimality over all the dimensions of policy in the policy space. And in terms of this issue of overly favoring the rich, it's not like it's a full-scale social welfare function by any means, but it does have a one person, one vote principle. And so there's a kind of rough and ready equality to it, as Nicolaus was talking about, the equality of points. Here you've got equality. You do have a one person, one vote principle, but with vector voting. And in fact, the more dimensions you're looking at once, the more likely it is to get you a reasonably good result. Because if you have too few dimensions, you're more likely to get a majoritarian result with the majority sort of overruling the minority on things. But if you have many dimensions, it's like one of the discussions in the Federalist Papers. You have different people with different interests going in different dimensions, and you're likely to get quite a good result. Okay, but the standard of comparison is actually not just the competitive market, but competitive equilibrium plus quadratic voting, certainly in this context. So this is a very quick layout of quadratic voting in a way consistent with our notation. So you have types theta, valuations, u of theta drawn from some distribution. Each individual buys votes. There's a quadratic cost of votes. We're going to normalize it this way. All voters receive a transfer. That's not too exciting. It's important for budget balance, but not otherwise. There's a probability distribution based on the votes, and that probability distribution is strictly increasing between 0 and 1, but you can actually achieve the 0 and 1 at finite levels of votes and of sums of votes. And so you get the valuation of the public good times the probability that it happens minus this quadratic cost of voting plus the transfer. Okay, now, very basic introduction to the normalized gradient addition mechanism. People get to do a vector vote. Now, in principle, you could have other shapes, but we're going to have S be a unit ball. You choose the point you like best out of a unit ball. What you're going to choose is a normalized gradient. So whatever direction, basically you're choosing your preferred direction, and then you get a vector of length 1. For simplicity, we're going to imagine weights of each person being 1. However, if you have any information about that, let's say you have half the information you need to do a social welfare function. Whatever information you have of that sort, you could use to try to give weights to people that might, for example, take into account that somebody was desperately poor and maybe you want to give them more weights. If you're ignorant about things that, if you don't have no information towards if you have all the information towards a social welfare function, you can just do that. If you have no information, then you probably want to do equal weighting. Okay, so this is just to illustrate what we mean by iterative. You're going to have a vector field, you're going to converge on things. Sometimes you have more than one stationary point. These stationary points are exactly what Hilland and Zeckhauser were studying. And although they have a tâtonnement process, it's not at all like this vector field that gets you to a point. So we did a lot of simulations to study these things, and having multiple stationary points isn't common. It's maybe 15% of the time, for example, in simulations we did. It does happen. There's an example with more groups. We tried very, very hard in the simulations to create cycles. Couldn't do it. You could get things that were, spiraling very gradually to the center if you tried really hard, but we couldn't get cycles. It's not easy to prove that cycles are absolutely impossible, but if they were easy to find, we would have found them. So I'm going to basically assume that you can come to a stationary point. I think in practice it's quite unlikely that you would fail to come to a stationary point. We had a table when we sent the paper off to the journal. We had a table that said, here in our simulations, here's the frequency with which we failed to come to rest in some stationary point. And we had a bunch of zeros, and the referees and editors said, "Are you joking? Are we going to take space for a big table of zeros?" All right. Okay, so what this paper is about is how quadratic voting relates to NGA. So quadratic voting, QV, is a mechanism for deciding to whether to build a single public good. Now, in spirit, quadratic voting includes a broad class of things, and in that broad meaning of quadratic voting, NGA is one of those things in the broad category of quadratic voting. But from here on, when I say QV, I'm going to mean specifically what Lally and Weil are doing. They get, in large populations, incentive compatibility and efficiency, which I'll talk more about. NGA tries to do much more, but can be restricted to the problem of deciding on a single public good and relevant taxes and transfers, after which iterative policy adjustments are turned off. So in other words, if we restrict things, if we shrink NGA down to do exactly the context, to take the exact context and try to perform the exact job that quadratic voting in Lally and Weil is doing, then it ends up looking very similar. And in fact, I'm going to argue that Lally and Weil's QV is a special case of NGA, actually, when you restrict it down. In particular, NGA has a free parameter that yields QV in the limit at one end and majority voting in the limit at the other end. And so, of course, it's for other parameters, it's going to be somewhere in between majority voting and quadratic voting. So, but for us, this is very interesting because it's a convergence on the idea of quadratic voting from a very different direction. I mean, we started from the subjective well-being literature. There are these problems of social choice. came at some of the intuition that Hilland and Zeckhauser had, but then it still, as soon as you apply it to the specific problem of deciding on a public good, you're back to quadratic voting, but with some other surrounding possibilities and context. Okay, now one of the things that I need to clarify in order to in this discussion is I want to distinguish between efficiency and Pareto optimality. So leaving aside some details of what happens when you have exact equality, I'm going to call it efficiency as build it if there's some set of side payments that makes building it a Pareto improvement. And of course, if the sum of the valuations is greater than the cost, there is some set of side payments that will make that a Pareto improvement. And if the sum of the valuations is less than the cost, then there's certainly some set of side payments that will make it a Pareto improvement not to do it. Now, however, the way efficiency is used, you tend to use it for this rule whether or not those side payments are actually made. So a Pareto improvement has to do with the side payments actually being made, and efficiency is just they could be made. Okay, now in NGA, NGA has no concept of efficiency distinct from Pareto optimality, but there are sort of two different notions of Pareto optimality. So the Pareto optimality of a point is the familiar notion that you have a point in policy space. If no further Pareto improvements are possible, that's a Pareto optimal point. Pareto optimality of the mechanism is something else. Pareto optimality of the mechanism is the mechanism will not rest as long as there is any Pareto improvement. If there is any Pareto improvement, it will keep going and going and going like the Energizer Bunny until it finally comes to a stationary point, which is guaranteed to be a Pareto improvement. And in fact, the way you prove that it will keep going and going is a useful result in its own right, that if there is a Pareto improvement, it will always move in a direction that has a positive dot product with that Pareto improvement. Now, one thing you need to realize right away is there's no way you're going to be able to guarantee that a mechanism will go in the direction of any particular Pareto improvement, because often there are two different Pareto improvements that are in different directions, so there's no way you can go towards both of them. But we do have a result that you will go with a positive dot product in the vector sense towards any Pareto improvement. Okay, so I need to talk a bit about incentive compatibility. So in our work, we're actually de-emphasizing incentive compatibility a bit for reasons that I will tell you, and I know that's a big piece in this literature, but in the Lally and Weil work, once the probability, this is our understanding of the issue, and I'm sure Glenn has a deeper understanding. Once the probability has already reached 0 or 1, and votes either for or against what happens would be wasted, individuals no longer have a clear incentive to reveal their valuations. Hence, to guarantee incentive compatibility, you need to make sure that even ignoring the constraint on probabilities, no individual would want to vote so much as to go beyond the edge. So what the large populations are doing is just making, there's this tension between incentive compatibility and efficiency that kind of starts looking not like such a big deal when you have a large population and each individual, even if they swung their, with any reasonable amount of votes they'd be tempted to do, you swing it from one end to the other, it's still not going to make that big a difference on whether the probability of the public good. But there's going to be some epsilon in efficiency, or else you can't give people the incentives, because if they knew the public good would be built whatever they voted, then there's no incentive compatibility. So I think that's the source of many of the complications in the Lally and Weil paper is exactly this issue. So what about for the normalized gradient addition mechanism? In the context of the public good problem, incentive compatibility is there on exactly the same terms as QV, which is not surprising since the QV is a special case of the NGA in that context. In general, in NGA, feasible votes are finite, so it's typically easier than in QV to see when you're in no danger of going off the edge, but in the QV limit of NGA, it's exactly the same issue. Now, our normalized gradient addition mechanism is well defined when you hit the boundary. Actually, there are several ways you can do it. We're just going to do a simple projection that I'll show in a minute. Our normalized gradient addition mechanism is not going to be globally incentive compatible. We're not terribly worried about that because it can be implemented by using implicit policy votes. Rather than having people vote directly, which tempts people to be very strategic, we're asking people, hey, how happy are you? How much meaning in life do you have? And then using econometric inference for how much a policy is affecting people, partly so we can get what the policy is actually doing instead of beliefs that may or may not be accurate. But the other advantage is it's going to be tougher for people to know enough to be strongly strategic. I mean, the fact that we're using only ordinal data means that they can't just say a bigger number and get a different result because it'll get shrunk down to a vector of length 1. Another point that I've really marveled at that Ori Heffetz made is, you know, we have these unemployment surveys. There are a lot of people who care about the policies that are affected by unemployment numbers, whom you might think would have some reason to be strategic about that. And yet, we don't have widespread effect, people saying, hey, go out and tell people you're unemployed even when you're not, because then we'll get better policies. And the reason is simple, that would be a huge scandal. You know, so it's a little harder to be strategic about things where if you try to coordinate people on being strategic, it's a big scandal. And so what matters then is if there's a way to be strategic that's simple enough that everybody can figure out on their own. So there's in other words, incentive compatibility issues, there's a continuum of issues, and it's not just an either or thing. If you're talking about practical purposes, it matters just how hard it is or just how easy it is to find a way to mess up the system strategically. Okay, and you've got the same issues of free riding and wasted votes are similar to those in many other mechanisms. And those can be addressed partially by transforming the policy space, which is something I'll talk about. Okay, very tightly related to Hylland and Zeckhauser. Basically, Hylland and Zeckhauser are doing the steady state. They prove existence and Pareto optimality. Again, they don't have the same dynamics. They have a tâtonnement dynamics, which is quite distinct. Anyway, this is the foundational paper, but we didn't know about it till we did this. And Chung and Duggan also independently came up with what's in Hylland and Zeckhauser. They're studying the steady state. They find additional results. And so I find it interesting that multiple economists have converged on this same intuition. And if you include quadratic voting itself, there's a lot of people whose sensibilities are converging on this kind of an approach. Okay, here's how you constrain it. We're going to do it very simply, like if you go out of the space. By the way, you need constraints for something like the public good problem because it only makes sense to have a probability between 0 and 1. It's kind of, you could take the money you'd piled up for the public good beyond that and throw it away, but that's not a very good idea. So you basically, what the interesting range is constrained. So if we have a constraint, then, and you went off the edge, we'd just project back to the closest point in the space. And so this transforming the policy space is fairly interesting. So you have some degrees of freedom. You know, there can be a natural metric that comes from counting up dollars, and that's where we're going to go in the first pictures that I have. But if you don't want to respect that kind of a metric, you could squish the policy space in a given dimension, and then that emphasizes that direction by giving sort of very high marginal products of voting in that direction. Or if you stretch in a dimension, you're kind of de-emphasizing that. You've reduced the marginal product of voting in that direction so that that's de-emphasized. And so people are going to be, you know, in the directions that are squished, those are the directions people are going to be fighting it out over. And the dimensions that are stretched, you get clean valuations because it's, you know, I mean, this is in the spirit of things that are done often in microeconomics. We think of there being this dimension that's just money, and then there's some other small thing. Well, because that other thing is kind of small compared to the money dimension, you get really clean valuations. But as soon as you have a bunch of big things, there's no way to get totally clean valuations when you're worried about balancing a bunch of big things. And NGA tries to deal with that. Okay, so in general, the normalized gradient addition mechanism implies a nice non-monetary numeraire for valuation. So think of it the following way. Suppose you started out with p minus 1 dimensions, then add the pth dimension. And imagine that in the p minus 1 dimensions, you've already gotten to a steady state. Now you add a p minus 1 dimension, a pth dimension, and then the extent to which you vote in that new dimension is going to cost you something of your arrow in the p minus 1 dimensions. That's going to be a quadratic cost, or approximately a quadratic cost. And so it's not money, it's how much you're sacrificing in all of the other dimensions. And if if it's just one of p dimensions, you're still going to get quite a nice valuation. Okay, let's get specific about the application to NGA. So we've got our point P, that's not a probability, that's a point in policy space, ZW. It's got, this is the amount of money for the public good, or the expected amount of money for the public good if you have to end up having to randomize. That's a vector of the amount of money left to, the amount of wealth left to people for everything else. Each person's utility function is valuation times probability of public good, which depends on the Z, and this vector of the wealths. And Z is going to be restricted to 0 or the cost of the public good. Since this is iterative, generically we're going to get to build the public good or not. Occasionally, in non-generic cases, you're going to have to randomize. The mechanism will be stopped when Z equals 0 or Z equals C, and that's just to make it comparable to Lally and Weil, is the stopping. Now, in principle, this mechanism, you can keep it going, and that's going to be very interesting. If you do keep it going, there are going to be some curvatures that we're going to ignore in the public good case. We're imagining this public good case is small enough that utility looks pretty linear given the contributions you're going to expect out of people. But there, although I can draw the pictures of that, it's not really reasonable to think that things stay linear if you keep the mechanism running. It's approximately linear if you do stop when you get the public good built and it wasn't too expensive. Okay, V theta greater than 0 is going to be voting towards the public good. V theta less than 0 is voting against the public good. And Y theta is voting to transfer money to self. So we're actually opening up the door to these side payments. Okay, each individual weighs the cost of voting for the public good and the wealth transfers to self. You got to sacrifice a vote towards, Y is saying, give me money at the, evenly divide the cost from everybody else, but give me money. That's what Y theta is. And, but if you do more V theta squared, you got to do less Y theta. What's the cost of the votes? Well, it's, to a third order approximation, it's quadratic. Okay, so already we're very close to quadratic voting, unless the number of votes is very large. But I'm going to show you that there's a transformation of the space that will make this as good an approximation as you want. But even in any case, it starts out as a third order approximation, which is quite good. And so we've got this utility function, valuation times psi of Z plus the votes minus the quadratic cost of voting plus the wealth you start with plus some fourth order, something proportional to the fourth order of the number of votes. So some pictures. So here's, before we even put in the public good, we've got person one's wealth and person two's wealth, but since we're soon going to have the public good, I want to have the public good be up. So up is making the public good with everybody contributing equally. That's what the direction up means. Without the public good, you just divide what's left. You have some initial point. Maybe somebody has a pile of money to begin with, but whatever's left, the mechanism will divide the remainder of the pie evenly. Now we've put in the public good, so that's the cost C. You could take the cost C from person 1 or take the cost C from person 2. Either way, you get the public good built. Or if you go straight up, you're taking it equally from the two people. Okay, and this is so I can talk about directions, just superimpose north, south, east, west. Yeah, the main things you need to know, it takes a little while to get used to the graphs, but up is paying for the public good, equal cost from equal payment from each person to get it built. Down is public good not built, then you distribute the money saved equally. This direction is leave public good the same, but take money from 2 and give it to 1. This direction is leave the public good the same, but take the money from 1 and give it to 2. Okay, so here's the utility function in this space, because this is the amount of money for the public good, and that's the valuation over the cost. W is the wealth of each person, C is the cost of the public good, U is the valuation, and U is the money metric utility. Then you've got subscripts 1 and 2. Now, this is not so interesting, but just to be clear, I'm going to think about things in terms of these dimensions I told you. Keep public good the same, transfer money, or make the public good taking money from both people. And this is the thing to focus in on, is this gradient, because that's what the normalized gradient addition mechanism uses. So that's not important because we're in continuous time anyway. It's only the direction that you're modifying things that matters, and you run it till you get to the edge. So here's the interesting thing. If you value the public good more than half of its cost, your normalized gradient will be pointed up. So if you're willing to pay your share and a little bit more, if I knew your true valuation, you're going to want to point up a little bit. If you value it less than half the cost, you're going to point down. And this is just with 2 people. It's going to carry over when there are n people. It'll be an nth of the cost. Okay, and so that's pretty sensible. Here's how the gradients look. The next slide is the normalized gradients. But here, just to be clear about the directions, so if you go straight up, going straight up is what you want to do if you value the public good infinitely. It's like, yes, you still would like money, but that's lexicographic. You basically just want to get the public good to happen. If you're willing to pay for the whole public good, then you still would like to, then your dearest wish would be for the other person to pay for the public good, but what you're indifferent to is you paying for the public good. And if you're willing to pay half of the public good, then you're actually indifferent to whether the public good happens with equal shares being paid, but you want to redistribute toward yourself with no change to the public good is your fondest wish. Then if you don't care about the public good at all, then you just want more money for yourself. You don't care about the public good, you want more money to yourself. And if you really, really hate the public good, so I imagine this as an opera house, you just hate opera music, you think that opera house next door, I die, then you point straight down. Okay, normalized gradients. Now, that's what the normalized gradients look like. You make them all the same length. And here's some examples. Person 1 values it the whole amount. Person 2 values it a bit too. It's going to be built. Here's what it looks like. You do have some side payments. It isn't just the public good is made. There are some significant side payments here. Here, person 1 values it at half the cost. Person 2 values it at a quarter the cost. It's not going to be built. Now, with 2 people, you're always going to get efficiency. That doesn't carry over to n people. But with 2 people, you're always going to get efficiency. Here's person 1 values at 3/2 the cost, but person 2 doesn't like opera music. But how much can you hate you hate opera music, but it's like, how much you're willing to pay not to have opera music. It's not enough to stop it from being built, but you kind of have a bit more side payments. Okay. And case 4 is a tug of war. Person 1 values it at 3/2 the cost. Person 2 values it at 1/4 the cost, and you're stuck at the status quo, and you're going to have to randomize. Okay, I've got to steal a minute. So here's the original metric. Now, if you stretch in this direction, what's going to happen is, because the marginal product of voting in this vertical direction is less, now that it's a long distance, now the normalized gradients will be more nearly horizontal. And so remember, we had a third order approximation that was very good as long as you didn't have too many votes. I can guarantee that the number of votes you're going to want to do will be quite small, and so the approximation will be arbitrarily good and close to quadratic voting by stretching in this direction. If you do this instead, you're going to wind up with majority voting, and you can show that a little more formally in this slide. Okay, I better go for, well, and there's the conclusion. So in addition to serving as one approach to the social choice problem, in the context of comprehensive evidence-based government, NGA can be applied to more limited contexts. The way more limited contexts are modeled in other works, such as in Lally and Weil, has implicit agenda setting built in. In NGA, the free parameters associated with agenda setting are explicit as the parameters describing transformations of the policy space. Applied to the problem of whether or not to build a particular public good, with further policy modifications stopped thereafter, it yields QV with one transformation and majority voting with the other. That's the stretching and squishing. Even when it doesn't implement QV, it's going to be Pareto optimal as a comprehensive social choice mechanism. So anyway, I'm happy to ask lots of questions, and I even have slides prepared for certain questions that I'm predicting. In fact, this asterisk is tempting you to ask a question about that one. Absolutely. Okay. So here we go. So I have to remind you of the difference between efficiency and Pareto optimality that I talked about before. Okay, so when you have, so we've got a proof. I'm going to prove that, I want to prove that the NGA mechanism, even in the constrained case, is Pareto optimal. It will not rest as long as there's a Pareto improvement. And I found this proof fun. So I need this concept of Kuhn-Tucker gremlin. So remember your first semester of graduate school in economics if you are an economist. And I'll show you pictures that will correspond to this. But this gives you the name Kuhn-Tucker gremlins. But we're going to have the constraints be G1, G2, or through Gn have to be non-negative. So here's the picture of the Kuhn-Tucker gremlin. Suppose the mechanism. So I'm adding up these normalized gradients. Suppose you went off the edge. You're required to be in this region. Then you just go back to the nearest point. But that nearest point is there's like a gremlin that really wants to be on this side of this constraint, and a gremlin that wants to be on this side of this constraint. That's a way of personifying the Kuhn-Tucker conditions that we're all used to. And it matters, same deal if you start from inside but go outside. Why is the mechanism Pareto optimal? It's actually very simple, because if that's a Pareto improvement, then my gradients have to point to it. And you can see that clearly if you just remember what's really meaningful is the indifference curves. And the indifference, locally, the indifference lines have to be orthogonal to these gradients. And so if there's a Pareto improvement, the gradients all have to point up or at worst sideways. And so you add those all up and it'll definitely point up. And I've just normalized things so the Pareto improvement is up. Now you might say, well, what about if there's curvature? It's the argument I gave before. If there is a distant Pareto improvement, that implies that going a tiny distance in that direction is also a Pareto improvement, and then so you can use the linear approximation. Okay, so here's and then here's the argument if you have constraints, basically without getting too much into the detail. What happens is if it's a feasible Pareto improvement, the basic intuition is the Kuhn-Tucker gremlins have to be reasonably happy with it, because it's inside the space, and the Kuhn-Tucker gremlins basically care about being inside the space. So there's some details. you've got your Kuhn-Tucker gremlins at the initial point that definitely think that it's that Pareto improvement is nice because it's feasible, and then because it's in continuous time, when you go to the new point, you're only going to be a little distance away, and so if it's curved like this, you're going to have, if this purple gremlin at the starting point liked it, then the close cousin gremlin will still like it. What if you're just barely indifferent? But if it's a straight line like this, which is the only case where exact indifference would come in, you get an exact clone gremlin. So this one is also indifferent. So basically, the real live people think it's a Pareto improvement, but in addition, these gremlins that only care about staying within the feasible space also like it. And so that then tells you that the mechanism is always going to move towards any feasible Pareto improvement. So it's guaranteed to never rest as long as there's a Pareto improvement. Okay, yeah.
So I had a comment and then a couple questions. So the comment was, so first of all, the notion of incentive compatibility actually doesn't show up in the paper with Steve because it's not a direct revelation mechanism. So there's simply no such thing as an incentive compatibility constraint. There's an equilibrium of the mechanism. That equilibrium is either efficient or not efficient. Incentive compatibility just isn't well defined in that.
Wait, couldn't you view it that way though? I mean, wouldn't that be a possible way of viewing your mechanism as from the lens of, you could kind of use the revelation principle and view it that way?
The thing is that that's not how it's analyzed. So there's no separateness of incentive compatibility and efficiency. It's just a statement that the equilibrium of this mechanism is efficient. And in terms of the incentives in the mechanism and what could lead to an inefficiency in the equilibrium of the mechanism, I don't think it really has to do with going off the edges of the choice. The real thing has to do with actually something that's subtler and higher order, which is whether everyone faces the same chance of being pivotal. So it's not whether the chance of being pivotal is too small, it's whether it's different proportionally across people. So in fact, the chance of being pivotal can be arbitrarily small, and yet it can still be the case that everyone perceives it in proportional terms to be extremely similar across people.
Oh, but if you're guaranteed to not go beyond the edge, then everybody is 100% pivotal. So that's where I was coming from when I talked about that.
Pivotal is what's the amount by which an additional vote increases the chance that the choice goes in your direction versus in the other direction. And it's that has to be similar across people in order to get efficiency and equilibrium. And it has nothing to do with how large in magnitude that quantity is. It's all about the proportional differences across people in the magnitude of that. And so that's all the subtlety in proving the results about quadratic voting. And I view that as like a price. So the way I would view this, and this relates to the incentive compatibility in your context, which is the way I think about this is it's like a price. It's not whether the price is 0 or infinity. The real question is, does everyone face the same price? Because if everyone doesn't face the same price, like, a monopolist effectively perceives a different price than the rest of the market does. If everyone doesn't face the same price, then you don't get efficiency. And analogously in your setting, the real issue with incentive compatibility to me, it has nothing to do with going off the edges. The problem is I might distort the vector that I report in order to push things into a different part of the space, which then, once people are in that part of the space, might be advantageous to me. In the same way that Roberts and Postlethwaite, when they were studying incentive compatibility in general equilibrium context, worried that people might manipulate their Walrasian demand vectors in order to manipulate the process of.
So in our case, you're going to get incentive compatibility if you do the following. So you say, whatever I vote, I still have a probability that's between 0 and 1, and so I'm not able. Any one individual is not able to vote off the edge. So as long as each individual. No. I'm just telling you where you would get 100% incentive compatibility in our mechanism.
But I don't think that's true, and the reason I don't think that's true is because of the Roberts and Postlethwaite type issues. Because I agree that if you were going to stop at the current point after the next iteration, that's absolutely true. But the thing is, if I know that by moving things into a different part of the space, I can change other people's demands and therefore lead us to end up somewhere different potentially.
No. But things are, when you have the linear preferences, then if you have the, because this is kind of local, you have the linear preferences. So there isn't some issue of a different part of the space being different. Unless you hit the edge, there's no difference in the way the space looks. It's all the same. So there isn't that danger.
I'm not talking about the specific application. I'm talking about your mechanism in general.
Oh, yeah.
So the point is, like, the incentive compatibility issue to me is really about the Roberts. It's really about this Robert and Postlewaite thing.
Yeah.
It's that, like, you in a Walrasian market, if you're not an infinitesimal agent, you want to manipulate your demand vector to allow the market to settle on a point that's more advantageous to you.
Yeah.
Even though
right.
once you're there, you want to report.
And the main point there is, and there's no way that our mechanism is incentive compatible in the large, and so the main point I made there is it matters whether the strategic things you can do to take advantage of the lack of 100% incentive compatibility are easy to deduce or hard to deduce.
No, I agree. I just think that the source of the non-incentive compatibility is different than what you were. I think it more has to do with.
Oh, no, that's in the global mechanism. I was really, when I said that was about the limited application. Yeah.
So then the questions I had was, could you describe the differences between your Tadema and the Hillen and Zeckhauser Tadema?
Well, that's a good question for. Do you remember, Dan? Yeah.
Since the mechanism wasn't fully described, I haven't read this up before. Is this revelation done sort of infinitesimally and continuously? So
yes.
You move a little bit of direction, then when you have to
yes. Yeah, absolutely. Yeah, absolutely. Yeah. Yeah. Now, in practice, in the real world application, you would move. You'd move a little bit. It wouldn't be infinitesimal, and then you'd measure next year, but it's going to be pretty close to that.
When I'm hearing what Glenn was saying before about manipulation. The notion, like especially when there's more than one place we could end up.
Yeah.
The idea that I might not want to move in my direction, but I want to move in a place that we then end up at a.
Oh yeah, no. If you knew a ton, there's no question. There are cases in our mechanism globally. If you knew everything perfectly, then you manipulate things a little bit, and then you can go to this stationary point instead of that stationary point. So there's no way it's globally incentive compatible. But what we can hope is that it's very subtle what you would have to do and very difficult to deduce, and it would take more knowledge than you have. And then the fact that it's locally incentive compatible if you just went a little ways and then stopped the mechanism. That indicates there aren't super easy ways to game the system.
Clarifying thing that probably connects back to I know a lot of Glenn and his co-authors work on QV. I know in his world, we have common knowledge about the distributions and things like that. So when people are playing the game and solving for equilibrium, they all have the same stuff in their head. When you talk about it being difficult, are you imagining that people know their own and know nothing else, or are you imagining?
Right. Our mechanism works best, in fact, if people know their own and don't know anything about anybody else's. That's the best case. Now, in this strict application, the knowing the distribution would matter not for the individual voters, but it would matter for the person setting up the mechanism, so they'd know how long do we run it before stopping it, so that we avoid this incentive compatibility problem of running off the edge. If you know the distribution, you know exactly how long to run it. If you have a large population and you know the distribution, you know exactly how long to run it, but that will still guarantee you have perfect incentive compatibility and only epsilon inefficiency from. You have to give people an epsilon probability that their vote against it will make it not happen, even if it's efficient, so that they have some incentives. But that's only an epsilon probability. Yeah.
I think your mechanism, it becomes most persuasive when you talk about the simplex of a budget allocation and this kind of process of and then we see this process where people could be assumed to have linear preferences if all votes are as long as votes are taking us in a neighborhood of the current budget allocation across which is really where you ended up.
Well, actually, I think the advantages of NGA really come out in cases where things are nonlinear. This that's originally where we were coming at it. So the simulations we did had people have a bliss points in policy space. It's, although you might want,
I'm sorry,
yeah.
locally, the
Yeah.
current vote is perceived to be only a vote over a small change.
Right, exactly. Yeah, local linearity definitely is important.
But when this process converges to a Pareto efficient budget allocation, the political spending doesn't stop. They have to keep. If you said you stop the process, but you don't stop the process. I mean, as a serious suggestion about a political system,
Yeah.
the
You keep
politics-
going. Yes, no, that's how we would use it.
Of course. So, but what I'm trying to get to is there's a cost of staying in place, which is not surprising that when a country has reached a Pareto efficient budget solution, the conflicting interests of different groups, they have to keep spending money they have to keep having political spending to keep to convey the signals that we still want to stay here, that our interests are this way and their interests are that
Yeah.
way. I think you want to talk about the trade-off between, so there are parameters that can increase or decrease the cost of politics at a Pareto efficient solution, and it's got to be the parametric changes that reduce the cost of politics at an efficient solution also slow down the process. Let me just finish.
Yeah.
Also
Yeah.
slow down the process of converging. That's got to be.
Well,
what the
let me
result is.
talk about
There's
this.
a trade-off between a system that
this-
reduces the cost of politics in the steady state
Yeah.
and one that converges
Well, this
quickly to
is an interesting question, actually, because this is not a question we've talked about before, but I do think the NGA mechanism is interesting. So I think of it not so much as, it does do the politics, because you have to do the politics, but I see it as primarily evidence-based government. I mean, the NGA mechanism is, I think it's going to be worth the cost of the data collection and data analysis and so on, because it's searching out Pareto improvements that you might not have suspected are there. There are certain things that are in the political discussion that political entrepreneurs have focused in on, but I'm sure there are Pareto improvements that nobody's talking about because nobody knows they're there. And the NGA mechanism is going to search them out.
You may want your paper to have a section that says, hey, look at this model. It shows how a political system which can more flexibly implement changing preferences of the population also it becomes a system which is more expensive to operate when those preferences aren't changing. That's all I'm trying to say. That would be an interesting section to add to your paper.
Yeah. I mean, go ahead.
If it's true.
Could you just make it more concrete and explain how this might work in a real political system? What the government would do?
Yeah, so we're working with the government of New On the subjective well-being measurement side. So suppose you take a government that says, hey, we'd like to measure national well-being, which New Zealand has. And so I spent 3 weeks there, and what I was talking about was evidence-based government. So you get this well-being data, then you have to combine that with randomized implementation of government policies. When you have a new government policy you're thinking about, you roll it out earlier in some places than others. This is just a matter of actually getting evidence. Then you see which things make people say they're better off than other things. And we're trying to be sophisticated about better off, because it's not just life satisfaction. You've got, in practice, you'd have, say, 120 dimensions of subjective well-being that you get weights of by stated preference weights. So we have some papers about this. So you have stated preference weights that basically tell you then when you can see, well, this policy makes this person say they're quite a bit better off. This policy says they're, less well off. And so as you, so what we proposed there in New Zealand was to have a web you have a web survey. So you have a web panel collecting this data, and then eventually you have a government agency that's, in addition to collecting the core subjective well-being data, then you invite social scientists to come in and propose additional data that's going to help them do causal inference. So that's not an easy thing. But if you have a rich enough data source, you can get the best social scientists in the world to help you do causal inference about how much will this policy do for this subgroup. In principle, you could do it at the individual level, but we're imagining in practice you'd have narrowly defined subgroups and say, does this policy make, you know, whatever, young Maori better off, for example, and then each subgroup gets a weight based on the number of people in that subgroup, and then you have a recommendation. This is what the mechanism would say. I'm imagining in practice you have the standard electoral politics, but you have an agency whose prestige grows over time that says, here's what the mechanism would say. This is the direction of modification that it's recommending that would, whatever language you want to do, that makes most people better off and that people have voted for. And so that has a lot of prestige and then influences the sort of regular political process. Now, New Zealand's interesting because it's a very agency-based government. You know, you have the parliament, but they basically say to the agencies, here's what we want to try to accomplish, you figure out the details. So you know, you actually could imagine it working that way there. Yeah.
So I'll ask the other half of my question, which was, so you said that both majority rule and what QV would implement could be Pareto optima under different transformations.
Yes, that's the next slide.
The reason I don't understand that is that you, as you said, if transfers are available, which they are in the way you've set things up, then there exists a unique Pareto optimal choice between whether to build the public good or not, though there exists a continuum of multidimensional continuum of Pareto optima in terms of the allocation of numeric.
Yes, I puzzled about exactly this question, and that's where these slides came from. And I was hoping you'd ask that. So here we go. So it's this fact that, the mechanism will not rest as long as there's a Pareto improvement. But that doesn't mean it'll take a particular Pareto improvement. After all, I gave the example, sometimes there's a Pareto improvement here and a Pareto improvement there. You can't go exactly towards both of them. So, okay, so now in these pictures, again, I want to apologize for the fact that this is way more linear than anything that's reasonable. It just shows how the math works, okay, how this is logically possible. But I don't take this seriously. The mechanism doesn't look great here because things are way too linear for large movements. But here's a case where, okay, as soon as you have three people, it's possible for this is a case where it's possible to have not building the public good be efficient. However, there's one person who really wants it not to happen. And so with the normalization of the gradient, that person's weight kind of gets down-weighted because they're going a lot in that direction, the quadratic, But then there are two other people who want to go up. So the majority vote would go up. The efficiency would go down in this case. So here there's enough of and you're somewhere in between majority vote and efficiency, so you're actually going up. The majority vote is winning a little bit. Imagine the majority vote aspect of it winning just barely. Okay, so then you go over here, you hit this end, and then the interesting thing is once you hit the boundary, this is going to go down and you're going to not build the public good. But basically the person who didn't want the public good used up all their money to get there. So you do get the efficient result in the end, but only after you hit the boundary. Now, an even more interesting case is this following one. Okay, so that one, again, it's extreme, but the math works. Okay, so it's not inconsistent. Okay, now this one is even more interesting, and again, it's extreme, but it shows how this is mathematically possible, what you're asking about. So this is a case where one person badly wants to build the public good, or not badly, but medium. There's one person who's pretty strong towards, two people who are against, but there's enough of the majority voting that you're actually headed down. Okay, and again, the person who cares a lot, they just get shrunk because they're carrying a lot. If they were just carrying a little bit, they wouldn't get shrunk. So, and actually, you can see it here. This person is kind of losing money, and then we have it in this other cross section. Now what's going to happen here is you're going to hit this boundary and then go down, and you're going to wind up at this point. You might say, oh, but it was efficient to build it. But that's a Pareto optimum, because this person, there's no longer any possible transfer. This person has no money left. So the person who values the public good enough that it would be efficient to build it is out of money.
Imagine we have more than 3 people. Imagine we have 1,000 people in this thing. What you're basically saying is that to the extent that you end up implementing majority rule, and imagine we've got a small minority, maybe 100 people, who care more than the 900 people, and so in order to get majority rule, all those 100 people are going to have to lose all of their money.
Again, I don't take that seriously, because what's going to happen is that as their monetary valuation of it is going to change as they get less money. And so what's going to happen is this is actually not such a silly outcome once you put some curvature, because suppose there are these super rich people who want to do it, okay? And so then it says, hey, you really want to do this, you're being outvoted by many people, and so they kind of lose money. And then as they get a little poorer, they say, you know, I don't know if I can afford this public good anymore. You know, remember, whether it's efficient or not depends on how wealthy the different people are, because the dollar valuation is, you know, it's not like the public good is some fixed number of dollars worth it to me. It's worth this many dollars if I'm rich, this many dollars if I now have less money. And so what...
How can that be a Pareto improvement over the original point?
No, be very careful. You're guaranteed to get to a Pareto optimum. You are not guaranteed to get to a Pareto improvement over the original point. See?
I thought you had said that.
No. You will always go towards a Pareto improvement, but you know, being 89 degrees off from the Pareto improvement is possible. Positive dot product towards a Pareto improvement, but basically, you could be doing a lot of other stuff. See, our mechanism is very sensitive to, like, trying to do some redistribution as well as efficiency, and it might be that's the big thing it's doing.
Well, just to clarify something you were saying before. So when I was asking the question about what do people know and what do they see, do they like understand?
Yeah.
So if I'm these rich people in Glenn's example and in your version of Glenn's example, if I'm these rich people, by following this mechanism, I've given away a lot of my money, and I've not gotten
absolutely.
the good that I've wanted.
Yeah.
So if I saw any of this coming, I wouldn't be doing it.
Yeah.
So we
and
require people to be my.
And I actually think there's a very simple manipulation, which is just demand reduction. I mean, there's anyway.
I don't think so. No, the more dimensions you have and the more things going on and the more curvature, the more reasonable our mechanism is going to be. So you want diversity of interest, you want curvature, you want a lot of things going on. If it's too simple, it's not going to be a good mechanism. You know, I mean, in these restricted contexts where it might do fine, but it's only robust if you have a diversity of interest and a lot of stuff going on.